Module 2, Lesson 1, Formal Logic. By definition, formal logic is the simplest variant of your propositional logic. A proposition is a simple declarative statement that is either true or false, but not both. Which of the following then is considered proposition? Number 1, yes, it is a proposition. Number 2, no, this is not a proposition, because we cannot distinguish whether this is true or false. Number 3, yes, this is a proposition, although this proposition is false. Number 4, no, this is not a proposition. Number 5, yes, this is a proposition. Therefore, it simply implies that mathematical statements are propositions. Number 6, no, this is not a proposition, simply because we cannot determine whether this statement is true or false because we do not know the value of x. Number 7 is a proposition, although this is false, while number 8, no, is not a proposition. Letters are often used to denote propositions, like P, Q, R, along with their corresponding subscripts. They are very similar to your Boolean or logical variables, which are denoted to be either true or false. This is one such example. Your proposition P denotes, I go to Harry's. Your proposition Q denotes, I go to the country, while your proposition R denotes, I will go shopping. Since the language is often ambiguous, therefore, the meaning of the words eventually can vary from context to context. Therefore, different propositional connectives used to connect your corresponding propositions are not defined using English text. However, a precise definition of your corresponding propositional connectives are given by what you call truth tables. Truth tables display the relationship between the truth values of your proposition and are especially valuable in the determination of the truth values of proposition, which are constructed from simpler propositions. A compound proposition is constructed from a logical particular connective and other propositions. In return, it is similar to your Boolean expression or Boolean function. By definition, your Boolean function f and g of n variables are equal if and only if their corresponding functions are equal. Two different Boolean expressions that represent the same function are equivalent. What are the different propositional connectives that are used for your corresponding propositions? You have the negation operator given off by this corresponding symbol. The negation proposition is a corresponding proposition that inverts the corresponding truth value input on your corresponding connective. It is commonly called the NOT operator. It is actually defined using a truth table, which eventually looks like this. So, if the propositional value is false, then the output seen on the right column becomes true. If the input proposition of your corresponding value is true, then the output of your corresponding negated proposition becomes false. Likewise, it is also defined by this logical truth table. The logical truth table displays the same information as your truth table, except all values of false are represented by zeros and all values of true are represented in 1. Let's take, for example, this given particular proposition. P denotes the earth is round. Then negation P denotes it is not the case that the earth is round, or more simply, the earth is not round. So when you apply negation connective on statements, you simply insert the keyword not into your statement. What is the negation of the proposition P if the proposition P denotes today is Friday? Therefore, the negation is today is not Friday. What is the negation of this proposition? Therefore, the negation of this proposition is you are not older than 16 years old. Another corresponding connective is known as the conjunction operator given off by your corresponding symbol. This particular connective joins together two propositions and is often denoted as the AND operator. The output of this proposition is true when both P and Q are true and is false otherwise. Therefore, when defined on your corresponding logical truth table, you would end up with four possible valuations, since this particular proposition involves in two propositional letters. If we then show all possible values of your propositions, therefore, you'd end up with possible values for P false, Q false, P false, Q true, P true, Q false, and P true, Q true. And according to the definition of your conjunction connective, the outcome of your conjunction connective is only true when both P and Q are true and is false otherwise. This is also seen on your corresponding logical truth table. Let's take, for example, that proposition P denotes I am at home and proposition Q denotes it is raining. Then, when you apply conjunction connective on these propositions, it then denotes I am at home and it is raining. What if your proposition P denotes you are a computer science major and your proposition Q denotes you are a freshman? If you apply conjunction connective on these propositions, you'd end up with you are a computer science major and you are a freshman. The disjunction operator. The disjunction operator is commonly called the OR operator and again placed between two propositional letters. The outcome of this connective is false when both P and Q are false, and then this is true otherwise. Therefore, your disjunction connective will have these corresponding truth table. Much like the truth table of your conjunction connective, there would be four possible valuations since this corresponding connective involves in two propositional letters. And according to the truth table, the outcome of your corresponding disjunction connective is false only if P as well as Q are both false. It is exactly the same corresponding value seen on your logical truth table. The use of the connective or in a disjunction corresponds to an inclusive manner. When you say inclusive manner, let's look at this given statement. Students who have taken calculus or computer science can take this class. Meaning, from this given particular sentence, it was implied that students who've already taken calculus are able to take this class. Likewise, students who are computer science major can also take this class. And it was also implied that students who've already taken calculus and at the same time are computer science major students can likewise take this class. Another connective is known as your exclusive OR, given off by this symbol, and is placed between two propositional letters, again, P and Q, and the output of this corresponding proposition is true exactly when one of your corresponding input propositional letters P and Q is true and is false otherwise. The other way the word OR is used in English is basically an exclusive manner, which is applied for exclusive OR. This particular statement is one such example. Soup or salad comes with your entree, meaning you could only have either the soup or the salad with your corresponding entree. And it's implied that you cannot have both soup or salad. Hence, the truth table defining your exclusive OR is given off by this truth table and this logical truth table. The next connective is known as the conditional or implication. An implication is again placed between two propositional letters. However, the proposition on the left is often called the hypothesis, antecedent, or premise, while the proposition on its right, which is often called Q, is referred to as the conclusion or consequence. The corresponding truth table for your particular implication states that you will only have an outcome of false when P is exactly true and Q is false. Therefore, you'd end up with this truth table and this logical truth table. Implications usually arise in many places in mathematical reasoning. Thus, a wide variety of terminology is often used to express your implication, and some of them are if then, P implies Q, if PQ, P only if Q. Other ways of expressing implications are P is sufficient for Q, Q if P, Q is necessary for P, Q and P, Q whenever P, a necessary condition for P is Q, Q follows from P, a sufficient condition for Q is P. In mathematical reasoning, implication is considered in a more general sort than in English. The mathematical concept of implication is independent of what you call the cause and effect relationship between hypothesis and conclusion. Hence, in the implication P and Q, there's no need for any connection between your antecedent or the consequent, meaning the truth value basically depends only on the values of P and Q. Therefore, it's perfectly fine if you eventually end up with the following implications in discrete mathematics. If the moon is made of green cheese, then I have more money than Bill Gates. Looking at this corresponding statement, basically, it makes no sense. However, in your corresponding discrete mathematics, as long as the truth value for these corresponding statements are evaluated, then this is still perfectly fine. Another example is this, or this. One way to view logical conditioning is to think of it as an obligation or a contract, which eventually means like this when you're campaigning, or this based on your instructor. As seen from this statement on the first statement, if the politician is elected and does not lower taxes, then the voters can say that he or she has broken the campaign pledge. Something similar holds for the professor. This corresponds to the case where P is true and Q is false. From your implication, it's possible to form new conditional statements, like the converse of your implication, the inverse of your implication, or the contrapositive of your implication. One such example of these different combinations would be if your P denotes today is Saturday and your proposition Q denotes I have a test today, then the implication is denoted as if today is Saturday, then I have a test today. The inverse of your implication would be read as if today is not Saturday, then I don't have a test today. The converse of your implication will read as if I have a test today, then today is Saturday. And the contrapositive of your implication will read as if I do not have a test today, then today is not Saturday. Note the difference of these corresponding statements eventually will have different meaning. Thus, the only particular corresponding similar statements here would be your implication and your contrapositive. The last connective is known as the biconditional or equivalence. The biconditional, given out by this particular symbol, correspondingly has an output of true when P and Q have the same truth value and is false otherwise. Note that the biconditional is precisely true when the implication and its corresponding converse is true. Due to this, the terminology applied for your corresponding biconditional will then be similar to your corresponding conditional or implication. However, it states that P if and only if Q, or P is necessary and sufficient for Q, Or you may state it using the if-then, but add the word conversely. This then is the corresponding truth table depicting your respective biconditional. Notice that the outcome of your truth table is true only when your corresponding truth values are exactly the same, as seen on this logical truth table. This is one such example. Let's take a look at how we use these corresponding connectives. On this given proposition, let's say P denotes Tom eats herb halibut, and proposition Q denotes Katie eats key lime pie. Therefore, if I negate P, it will then read as Tom does not eat herb halibut. If I apply conjunction connective on P and Q, it will state as Tom eats herb halibut and Katie eats key lime pie. If I apply implication, this will then read as if Tom eats herb halibut, then Katie eats key lime pie. If I apply a biconditional, then it will read as Tom eats herb halibut if and only if Katie eats key lime pie. And if I apply a more complicated expression by combining these different corresponding connectives, eventually you'd end up with a different statement. But note that there is hierarchy between your corresponding connectives. And the hierarchy follows that you have to apply the negation connective first, then followed by your conjunction connective, followed by your disjunction connective, followed by your exclusive or, followed by your implication, followed by your biconditional. That is, if there are no parentheses or brackets involved in your corresponding expressions, that tells you which connective should be performed first. So in this case, I perform the negation connective first by adding the keyword not on my propositions and then applying the word or your disjunction connective. Hence, the statement can be read as neither Tom eats herb halibut nor Katie eats key lime pie. In returns, also more complicated propositional expressions can be created by simply combining your respective connectives. And as a way of reducing your corresponding parentheses, you may see precedence of your corresponding connectives, as I have mentioned before. Therefore, this particular example is equivalent to this statement. If you intend to have this corresponding statement, then you must use a parenthesis on your expression. Your precedence of logical operators follows this corresponding hierarchy. There are different applications of your propositional logic. The first one is translating your English to propositional logic. The steps to convert an English sentence to a statement in proposition or propositional logic is: first, identify the atomic propositions. Then next, you represent each proposition using a propositional letter or a variable. Then determine the appropriate logical connectives and then apply that on your corresponding expression. Let's translate this corresponding English sentence into proposition. If I go to Harry's or to the country, I will not go shopping. We then denote P as I go to Harry's, Q, I go to the country, R, I will go shopping. After stating them and giving them each a propositional letter, we'll then highlight the corresponding keywords that are seen on the statements and then represent them using your respective connective. Therefore, if, then this will be your corresponding propositional expression. Let's translate this other example. You can access the internet from campus only if you are a freshman, a computer science major, or you are not a freshman. So I denoted A to be you can access the internet from campus, B, you are a computer science major, and C, you are a freshman. Therefore, according to the statement, I've highlighted the corresponding keywords associated with your connectives. Therefore, you'd end up with this corresponding expression. And I place a parenthesis showing that these connectives eventually are performed first. Let's translate the other corresponding English sentence. You cannot ride the roller coaster if you are under 4 feet tall unless you're older than 16 years old. Therefore, we identify each corresponding proposition and then assign a letter, in this case P, Q, and R, and then identify the corresponding keywords. As seen here, you have the keyword if, but you have also the word unless, which implies that if the person is under 4 feet, then that person is allowed to ride the roller coaster if that person is older than 16 years old. Hence, you'd end up with this corresponding propositional expression. The other application of your proposition logic is on system specification. Systems and software engineers take requirements in English and express them in precise specification language based on logic. This is one such particular example. The automated reply cannot be sent when the file system is full. Therefore, we simply denote P as the automated reply can be sent, Q, the file system is full. Therefore, you'd end up with this corresponding propositional expression. Another application of your propositional logic is on logic puzzles. Given here is one such example. An island has two kinds of inhabitants, knights, who always tells the truth, and knaves, who always lie. You go to the island and meet A and B. A says B is a knight, while B says the two of us are of opposite types. What are the types of A and B? The solution here is that basically the statements A is a knight and B is a knight respectively. So then if I represent that by negating P, and eventually the proposition that A is a knave and not Q, that B is a knave. If A is a knight, then P is then true, since knights always tells the truth. Q must also be true. Then P and not Q, or not P and Q, would have to be true, but it is not so. Therefore, A is not a knight, and therefore not P must be true. Hence, if A is a knave, then B must not be a knight, since knaves always lie. So then both not P and not Q eventually hold, since both are corresponding knaves. This ends the module.